All right, let's look at finite element method and its applications to Poisson equation. Let's look at Poisson equation. This is called Poisson equation. To apply finite element method, we are going to follow these steps. One is to multiply by a test function and integrate along the domain. So we are looking at 1D here, and therefore we are going to integrate along x. So the Poisson equation is like this for 1D, or we can say equals minus f of x. This is the Poisson equation. Now let the test function be, let nj be the test function. This nj is just a test function. Now we multiply, like we said, we're going to multiply it and integrate. So the squared sine, you can make it a normal derivative because it's 1D, times n j. What does j mean? J is like a family, right? It's one test function amongst a family of many test functions you can apply. So we're going to integrate. So let's say we're solving this problem for a domain from 0 to L, for example, and let's say psi of L is 0 and psi of 0 is 0. So this node 0 and the last node, the potential does not exist there. It exists within the middle nodes, node 1, node 2, node 3, node 4, and all those nodes. So this nj is a function that would exist within these nodes and would be an approximate solution we will see later. So for now we integrate from 0 to L dx. You are integrating in both sides. So equals minus integral from 0 to L f of x. Remember, for the electrostatics, f of x is rho over epsilon 0. Now f of x nj dx. So for the right hand side, for the left hand side, we integrate by parts. So what do? Let u, so I'll use another pen, let u equals nj. So nj is also a function of x, right? nj is also a function of x, and here du by dx would be the nj by dx, and then you can have du equals dnj by dx, and for the integration by parts, if this is u, then you can say dv is del squared psi by del x squared del x, such that when you integrate both sides, this looks like so the left hand side is just v, but this is going to look like this, del by del x of del psi by del x del x. And when you have a situation like this, you can call v equals del phi by del x. And because the integral is uv minus integral of v du, we have all the cards at hand. So now we can say that this left hand side is going to be uv. So uv is like, yeah, I forgot, there is also another condition that this test function should satisfy. Nj of 0 and nj of L should also be 0, because it's a test function, so it has to vanish at the points where the wave function, the potential vanishes. So you have here, so this one becomes uv. So uv is like u, which is this, so is nj of x, v psi by del x evaluated as 0 to L minus integral of v du, this is v, del psi by del x du is what? Del nj by del x from here. And this, all of this equals minus integral from 0 to L f of x nj dx. And what happens next? Because nj of 0 equals nj of x equals 0, so this term vanishes. What you have left is this term, and the negatives will go, as you can see. All right, so that's what we got. That is step 1. So what we did now here is just step 1. And that's what we see here in the, so that's what we see here. That's step 1, and which led to this. Now step 2 is, so I used nj as the test function. Now I have to compromise, because I was using nj here, unless I would like to use ni. I used nj all over. So if I may continue with my which would obviously contradict what we have here in the handout, but anyway, it's just the index. I and j are the same thing. So because you have this, let's get this guy, copy. Because you have this, let's paste it here. You now have this, you assume, so step 2, so that's step 1, we're done. So step 2, assume a trial solution psi. So we want to, we don't know psi, but we can assume a trial solution using basis function. In fact, the idea of finite element is to be able to have these functions that, so this is element 1, element 2, element 3, element 4. So we would like to have function. In my case, I will not use u, I will use ni. So we want to say that psi is represented by some basis coefficients psi I, which are what we will be looking for, and then some basis functions ni of x. So I is from 0, so this is node 0, this is node n, so node 0 to node n. That's what we are going to do, so that at 0 you have n0, at 1 you have n1, until nn. But don't forget, this is known for this problem, and this is known for this problem. But anyways, we can still have it. Now let's estimate the global stiffness matrix, but that will be the next thing to do. Now if you substitute this here, so that means so this means del psi by del x would be I equals to 0 to n psi I del n I of x by del x. That's what it's going to be, and therefore let's put it back in. So you have integral from 0 to L psi I. Let's put the summation here, I equals to 0 to n dn I by dx dn j by dx equals integral from 0 to L fi. You can call it fi or f of x, but anyways, f of x at I, because now you're in discrete form, times nj dx, and you can let some value k, you can let some parameter k, you can call it kij, so that I for this and j for this, kij equals 0 to L. Now dni by dx dnj by dx equals, oh no, yeah, and called some fi. Fi is 0 to L. This is f of x, right? So fi of x nj dx, and this yields something like this: I equals 0 to n k I j psi I equals fi. That's the matrix we would like to solve. This is in the form AX equals B, where the A is the Kij and the X is what we want to seek, and B is the Fi. Now this Kij has a name, so Kij is called stiffness. Just a name. The engineers, they give it a name, but it's just a matrix, but you call it stiffness matrix. And Fi is called the load vector. Anyways, and in implementation, usually you want to generate this and this matrix for any problem and solve the matrix equation like this. So any problem you have, you want to have it look like this, then you create this matrix and this matrix and then solve it. And that's what we have here. That's what we have here. And now how can we create this matrix? This is where it's very important for us to see. Now let's assume this is 0 and this is L. Okay, if there are, let's say there are 1, 2, 3, so there are 3 elements. So element 1, element 2, element 3, element 4. So you have here 3 elements. How many nodes? Node 1, node 2, node 3, node 4, node 5. No. Element 1, element 2, element 3, element 4. Okay. So we have 4, but I don't want 4 elements. Anyways, it's fine. So here we have 4 elements and 5 nodes. So if you have 5 nodes, that means you are going to have 5 by 5, because this is 0, 1, 2, 3, 4, right? So you're going to have K0, 0, K0, 1 until K0, 4, K0, 2, K0, 3, K0, 4, because it's Kij. Then you're going to have K1, 0, K1, 1, K1, 2, K1, 3, K1, 4, until you reach K4, 1, K4, 2, K4, 4. This is the matrix you want to build. How do you build this matrix? First, you need to know that Kij is an integral from, okay, so now it depends on how you're going. You can do the local and then you get the global. So the local is Kij. So if you're going 0, 0 is this point, 0, 0. 0, 1 is here, from here to here. So like this. So 0, 0 is a line like this. Just picture it as a line like this. So this is 0, 0. 0, 1, 1, 0, 1, 1. 1, 2, 2, 1, 2, 2, 2, 3, 3, 2, 3, 3, 3, 4, 4, 3, 4, 4. What do you notice? You notice that here you can have this is psi 0, or you can call it n0. Let's call it n0, right? n1, n2, n3, n4. Now n0, so kij is from, so we can call this x0, x1, x2, x3, x4. So kij, if you're looking at kij, you can move from xi to xi plus 1, right? So you're going to do ni, and nj will be ni plus 1. Anyways, all right, let me call this xi to xj, maybe, and then ni nj dx. But in practice, you cannot use j. You have to use, because when you say n k00 is like n0 times n0. So k00 is like, so you see, it's like from x0 to x1 n0. But I forgot something here, I think. Where is it? Where did I? There is, yeah, okay, so it's correct. So I'm going to write n prime here, n prime, instead of writing the n by dx, right? So let's make it n prime. So it's n prime 0, n 0 prime dx, k 0 1. You know what it means. From 0 to 1 is what? It's that's this line. The same. n0, n1 prime prime, x0 to x1 dx, k 0 2. There is no line connecting k0 and k2, so this is 0. It's not possible. And so between any two elements, you can only have two at a time. For example, 0 and 1 are connected. That's all. But 0 is not connected to 2. So if you k2 0 should be 0. 1 and 2 are connected, and 1 and 0 are connected. So if you're looking for k01 or k12, yes, it's fine. But you cannot have k13 because 3 is far. But you can have k23. You can have k34, and that's how it goes. So some of the elements will be 0. For example, k14 would be 0 because you're looking at k1 and 4. They're not close, and that's how you build a matrix. So now let's look at practically how to get the values. Now the fact that we have to define, because for you to be able to do the nj by dx, you need to first, what is nj first? So nj is something like this. This line that is going this way is where k0, so k0, I'm sorry, n0 exists here. You can call this line. So let's assume this has a width of 1. So this point is, this is x0, x1, x2, x3. So n0 exists between it exists between 0 comma 0, so that's like x0 comma x0, and also x0 comma x1. So it exists here, which is 1, and then it is connected like this. So usually you don't take the one that is here, you take the one that either is going, or you take the one that connects. You're looking at the connection. So n0 is like, it's like 1. So you can say literally, you can say y2 minus y1 over x2 minus x1, for example. And 2 is a function that is, no, this is not what we're supposed to do. First we have to define the interval h, because this would help in the explanation. Now n0 is, you see here is 1, and then this line is going down. So this line is like a negative slope. You can say it's like x1 minus x over h. So when you want to take the derivative, the n0 by dx, you're going to have minus x over h, because x1 is a value, right? And that's how you get n0 and dn0. We have this. Now we move to n1. n1 is here. This is n1. There is a line connecting n1 to n0, this line. And there is a line connecting n1 to n2. So n1 has this line. So this line is, because it's going up, you can say, so it's x, oh yeah, I forgot to give the limits here. This is from x0 to x1. That's the limit where n0 can be defined. But this one can be defined here for this line. You can call it x minus x0 over h. This is from x0 to x1, because this line is from x0 to x1. So from x0 to x1, that is it. And then this line that is going down is a kind of x2 minus x over h from x1 to x2, and that is n1. So you can get the derivative as well of n1. So the n1 by dx, you are going to have two derivatives. It's this guy, it's x over h from x0 to x1, and it's minus x over h from x1 to x2. And how about x2? Let's do x2 so you can get familiar with the process. We got, so now you should notice that we now have n1 and derivative of n1. We have n1 and we have the derivative of n1. We have n0 and we have the derivative of n0. Now let's move to n2. n2 is here. The same process. n2 is connected to n1 and is connected to n3. So n2 will have this. Remember, you're going this way, so is x minus x1, so is x minus x1 over h from x1 to x2, and is going down here is x3 minus x over h from x2 to x3, and the derivatives, you can easily get the derivatives. dn2 by dx gives you, for this one is 1 over h between x1 and x2, and for this one is minus 1 over h between x2 and x3. And now that we have n2, derivative of n2, it's easy for you to calculate. For example, k, let's do k00, for example. So it's going to be, these are the range, x0 to x1, so it's going to be x0 here, x0 to x1 of the, or I can just say n0 prime dx, and we know n0 prime, what n0 prime is. n0 prime is supposed to be 1 over h, not x over h, and this gives you integral from x0 to x1 negative 1 over h squared dx, and k00 gives you, when you do, so let's do it. You have, I know you can integrate this. This is easy. So let's assume we did all we did. You are going to have x2 x1 minus x0 over h squared, but x1 minus x0 is still h, as you can see. So you can say x1 minus x0 is still h. Even in coding, we code it like that. So that's like h over h squared, which is 1 over h. So the element in k00 here, you can make it 1 over h. So that means all you need is, now let's do k22, for example. Let's do k22 because n2 is here. So k22 is, here we have a situation because you're going to integrate from x1 to x2 of n2 prime delta x, plus you're going to integrate again from x2 to x3 n2 prime delta x. But we already know the, so that means you're going to integrate this 1 over h, so you're going to integrate from x1 to x2 1 over h times 1 over h, which is going to give you 1 over h squared dx, plus integral from x1 to x2, this is 1 over h, but it's squared, so minus 1 over h squared with the x. When you integrate this gives you k2 is, because we already did that, this is 1 over h, this is 1 over h, so you're going to have 2 over h, and then k22, so k22 here, k22 should be let's say k20, k21, k22, so this element here is 2 over h, and that's how you, so we already know what k1, k2, or let's say k34. So what does this mean? You're going to look at k34. K34 is, this is n4, and this guy is x minus, oh no, there is no k24, so I can only say k23. No, n not n1, n2. This is supposed to be n3, sorry. So that means I missed. We're supposed to stop at n3 here, so forgive me. Yeah, so we're not supposed to go to the font. Just stop in k33, that's the final one you're supposed to get. But why did I have, oh yeah, so I was using this one that has 4 nodes. I made them 3 here. Anyways, you get the idea. You get the idea. So k34, if it does exist, it's going to be from x2, sorry, from, let's do the one we can see, so I can show you exactly what happens. Where is it? Yeah, let's compute k23, because this is 2, this is 3. Now this line is x minus x2, because it's coming from x2 over h. That's from x2 to x3. x2 to x3. And there is this line that is coming down. So we have this line already, and there is this line that is coming down, which is x3 minus x over h. Let's do it in another color, x3 minus x over h. But this one is also from x2 to x3. Good. So in this case, you are going to look at this one. This is for n3, the one that goes up. And this is for n2, one that goes down. So you're going to do n2 prime. So the, let me see if I can get these guys. This guy is, let's cut it. Let's go somewhere here, just for you to see. Space it here. Now this is for, sorry, this is for n3, this is for n2. So k23 would be integral from x2 to x3, n2 prime, n3 prime dx. Now n3 prime is going to be Let's make sure that this, yeah, 3 minus, yeah, good. No, this is n2, sorry, because the one going down is for n2, the one going up is for n3. So this is for n3, that's x3. x3 minus x is for n3. Good. X minus x2. This one is x3 minus x. That is n2. This is going x minus x2. This is n3. Good. So we don't mix them up. Now n3. So this is so n2 prime is going to be, you take the derivative of this. This will go to 0. You have minus 1 over h. N3 prime would give you only 1 over h. And here you have to, so that's x2 to x3, and n2 prime is minus 1 over h and 1 over h dx. And what do we get? We get negative when you do the integral, because it's going to be 1 over h squared. When you do x3 minus x2 equals h, you're going to get minus 1 over h. So k23 is going to be 1 over h. So here it's going to be 1 over h. And that's how you generate the matrix. And when you do the same, you are going to do, because k32 as well, this is k23, which we did and got 1 over h. But when you do k32 is the same thing. So 1 over h will also come here. And in the end, you find the matrix looking like the K matrix. The K matrix would look like this. So you are going to have 1 over h outside. K11, if you remember, we got 1 over h. Let's see. Yes, we got 1 over h. So we're going to take h outside. And when you do the operation like I explained, you're going to have a matrix like this. So this is the global stiffness matrix, like this. 1 over h, this will be minus 1, and then the mirror will be the same. You remember? K00, K01, right? So K10, K10. So these guys will mirror, and then these guys will mirror. And as usual until here. And this is the global matrix. And that's how it's supposed to look like. For the f, now let's do f. So f I is integral from 0 to L fi of x, or f of xi I would say, times n, is it nj we're using or ni? Let's find, make sure that this is okay. So it's nj. So nj of x delta x. What do you do here? Like as usual, you will always, this function, if it is known, you will know the value of the function of at this point, fi, f of x0, f of x1, f of x2, f of x3, f of xn, and you already have n0. So let's call this I and j. It's just let's call this f j, so you can see the homogeneity. So you can have f0, and then you can multiply them. We know that for example, this guy runs from here to here, so we know that n0 is x minus x naught over h, because it's going down. No, it's going down, so x1 minus x is x1 minus x over h. Usually where the arrow is looking at, you do just where it's pointing at minus where it left. So x1 minus x, and you're going to apply here. So f0 would be integral from, this is x naught, x1, so you're going to integrate from x naught to x1. Fj, if you know the value, you put it. If you don't know, I think we can, let fj be 1, so we can see easily how. So it's going to be 1 times x1 minus x over h delta x. Now you're going to integrate. This is going to be, or let's just say we integrate, let's split. You're going to have x1 dx over h, x naught to x1 minus x over h dx, x naught to x1. This gives you x1x over h x naught to x1 minus x squared over 2h x naught to x1. This gives you x1 squared over h minus x1 x naught over h minus x1 squared over 2h plus x naught squared over 2h. And this leads to, yes, so but if we look at from where we started, this is 0, so x0 is 0 and x1 will be h because it's the next step. And if x0 is 0, this guy goes to 0, this guy goes to 0. Then with this guy, with these two guys, you have x1 squared over 2 h, and the fact that x1 itself is h, so what you're going to be left with is f0 is h over 2. The matrix f0, the matrix f, so the first element is h over 2. And if you continue this way, you're going to have other elements. Here would be so let's write it this way. Let's say h is it's outside, h over 2 it's outside. You're going to have here 1 2 2 two twos and then 1. This is how you're going to have your f. We already have seen how the k is generated, and this is what we explained here. So this is an example where you're looking at node 0, node 1, node 2, node 3, node, okay, only 3 nodes. You divide it into 3, So we have something like this. So in this case the length L is 1, and n0, now you understand why it is expressed this way, why n1 is like this, why n2 is like that, why n3 would look like this. And as I already explained, because you have length L, then you take h to be 1/3. So when you do the operation, you get this. I suppose now you understand exactly how we get k00, k10, k22, k3, and all those, and then in the end we build this matrix. Notice that we did not, we're supposed to have 1/h, but if you do 1/h, because h is 1/3, so 3 comes up, and 3 is, this is why you have 6 here, and so, because it's supposed to be 1/h, that's 1 over, so k is supposed to be 1/h, 1/1/3, and then 1 minus 1 minus 1, 2, dot, dot, dot. So but when you do the operation, you get what you see here. The force vector I already explained. F0 comes this way, F1 comes this way, F2 comes this way. So F is h/2, 1, 2, 2, dot, dot, 1 in the end. And that's why you have what you have here. And to apply the boundary conditions, we are going to solve ax equals b, and f is the b, and k is the a, and psi is the x. So that means if we say psi of 0 equals 0, that automatically will affect the dimensions of f and k, because they can no longer be, they have to be the same for the matrix multiplication to occur. And the matrix K was looking like this, but the fact that you are multiplying by a matrix that has 0 elements here and here, you're only going to have the ones in the middle. And applying the boundary condition reduces the K matrix to what you see here. And this is supposed to be psi, like the potential here as well. Now we are professionals, so here we have the problem defined. This is what we're going to solve in the code. We have psi defined at the ends. We're going to look at this, and we get 5 nodes. So 5 nodes and 4 elements, right? Node 1, node 2, node 3, node 4, node 5. We take h as this. Automatically you can build your, this is the matrix, and you build it like this. We already have explained in the code. This is what we're going to apply, inshallah. And you can build your F matrix like this, apply the boundary conditions, and what you get is this. Then you, because you're looking for the psi, you perform these operations, and in the end you get psi like this. Thank you very much.